Hey, welcome to our geothermal energy presentation. Geothermal is one of those energy sources that people don't necessarily know that much about, so we're hoping to fill you in on what it is, how it works, and the advantages and disadvantages associated with it. So if you break down the word geothermal into the two parts, geo means coming from the earth, thermal meaning like heat, and you've got what geothermal energy is about. So it's heat from the earth that we're going to use to help us make electricity, although geothermal sometimes is used to just mean heat from the earth that you could use to heat and also cool your house. So we'll talk about that at the end. There are three main factors that are contributing to geothermal energy. First, when the earth first formed from the early solar system, that gave it some initial energy, gave it a little bit of heat. So there's that. Second, radioactive decay of elements inside the earth is acting to keep it warm. And then third, sunlight comes down from the sun and it warms up the surface layer of the earth. Only the first two of those points, though, actually play a role in geothermal electricity. So we're going to just kind of detail a little bit more. So the leading hypothesis on where did our solar system come from has to do with how stars form. So stars form by a cloud of collapsing gas and dust, and as it compresses together, it begins to spin around. And that spin will lead to matter being ejected outward from that initial cloud collapse. We see this when we look into other parts of our galaxy. We can see that newly forming stars often will have this disk of gas and dust that surrounds them. And that suggests to us that that's likely how our solar system came together as well. And it would make sense that gravity over time would pull things together, causing collisions, things collapsing together, and eventually leading us down to our present day solar system. So that early Earth would have experienced a lot of collisions. It would have been a very hot environment with matter colliding in and collapsing together. And so there would have been some initial heat. Now, a lot of the other planets would have gone through this too, and therefore would have been hot initially as well. Some of those other planets, we look around and we see, well, they're not hot on the interior anymore, that they've cooled off. So there's got to be something more to Earth's internal heat than just Earth's early formation. And that brings us to point number two, which is the decay of radioactive elements. So if these elements on the interior of the Earth are going through radioactive decay, we know that that means energy is going to be given off. And so as the decay takes place, energy is released in the form of radiation, some of that gets absorbed, and it translates into random kinetic energy and therefore heat. So the inside of the Earth is getting warmed continuously by decay of radioactive elements. Now, if we look at, well, what are the energy transformations that happen when you use geothermal energy? It is simply by accessing heated rocks and heated water inside the Earth. You're taking advantage of that random kinetic energy and transferring it to water, and that's going to heat it up and turn it to steam. So in other words, it's just like coal power plants or natural gas power plants or even nuclear power plants in that something is heating up water, turning it to steam so that it spins a turbine and creates electricity, flow of electrons. So here's the typical way that you'd see it. Those regions of the Earth where there is molten rock closer to the surface, areas that have volcanism, areas that have hot springs, areas that have geysers. These are going to be places where geothermal electricity is going to be economically feasible. It's going to have molten material closer to the surface, and that means when it rains, that rainwater trickles down and will go through, infiltrate through the soil and then through some layers of rock and then get heated up by the molten material that's not too far down. So you have this pool of hot water that is not that far below the surface, which can be drilled into and pulled up to the surface, and that can be energy that is used to help run a power plant. If you look at, well, where in the world do we actually have geothermal power plants located, you can see the areas that are highlighted. So the volcanic regions of Japan and the Philippines. You also notice the west coast of the United States down through Central America, and then also Italy, and also over here, Iceland. These are locations which have a lot of power that is based upon geothermal energy, and in particular, Iceland is famous for the fact that it has quite a bit of geothermal energy being used. So once you have determined that this area is appropriate, the way that it would work is you would drill a hole, maybe 2,000 feet, perhaps up to 2 miles deep. And what would happen is you would produce a well where you're going to have a pipe where you're going to bring heated water up to the surface. That heated water is then used to produce steam, run a turbine, and make electricity. The water that you're condensing back out of it, some of it, as you can see, is being put into steam, but some of it is recondensed and injected back down into the ground to replenish the water that you're extracting out. So in terms of the benefits, once you build the power plant, like a lot of the other renewable energy sources, it's going to be free. You don't have to import fuel. You don't have to buy it. And so it's a relatively sustainable solution. We know that eventually the Earth is going to cool off and it's not going to have heat energy forever, but this is going to be a very long time into the future for any given location. So that is not considered to be a limitation on this as a resource. When you consider its consistency, it's going to work on a pretty consistent basis. The only factor that's going to possibly disrupt your consistency would be a lack of water, which is actually currently affecting some of the geothermal power plants in California because of the drought that they've had. When you look at the emissions to the atmosphere, we look at the picture here, you can see there's a lot of big cloud coming up there, but it's not anything other than water vapor. So that is the emission similar to nuclear power plants. So in terms of problems, well, the biggest limitation is you can't put them everywhere. You have to put them in places that have the geologic conditions which are favorable, and that means having a molten source near the surface. So a volcanic region, a region that's got geysers or hot springs, those are going to be places where you'll know that you could use geothermal power. When you look at the initial cost, it's going to be considerably more expensive than something like, for example, a natural gas power plant. However, when you consider the fact that you have to keep buying the fuel when you do a natural gas power plant, the costs kind of equalize out over the lifetime of the power plant. As far as groundwater changes, sometimes if you're not injecting the water back into the ground, you can run into lowering groundwater levels and running out of water. And the other thing is when you do re-inject the water down, sometimes that's been shown to see the same problems that we've seen with re-injecting wastewater from fracking back down into the earth, and that is you can trigger earthquakes. So studies have demonstrated that the injection of water into the earth can lead to increased earthquake frequency. A final thing to consider is corrosion of the pipes, because after all, you're working with water that's been heated up by a magma source, and there's going to be a lot of minerals dissolved in this water. So as you bring them up, and they're under very high temperature and pressure, and then you allow them to cool down, there's going to be a tendency for minerals to precipitate out, and so you are going to end up with scale building up on the pipes, as you can see in this picture, and that means that you're going to restrict flow through the pipes, and then the efficiency of the plants don't work as well. So maintenance is going to be necessary in order to keep it working in its best shape. Now, we had mentioned before that you need the ideal geologic conditions, and you might say, well, that doesn't seem like Connecticut. We do not have active volcanism in Connecticut. But you might have heard people talking about using geothermal energy for their house. And this is a different kind of geothermal energy. It's not the same as geothermal electricity. So here's how it can work. A common system for geothermal energy in your house would have a compressor unit probably located in your basement. And you would have the pipes going out of that compressor unit into the yard and kind of spreading out, maximizing surface area. Because what you're going to try to do is exchange heat with the ground. And the reasoning goes like this. So consider the winter. It's really cold outside, the air is very cold, and you want your house to be warm. So if you take a fluid and you have it at a regular temperature and you compress it, what we find is it's going to warm up. And so you could take a regular fluid, warm it up by putting it under compression, and warm it up and have a fan blow that off, and now you have warm air coming into your house. And now if you take that same fluid and you put it outside and you decompress it, it will expand and cool, and so now it's been cooled down a whole lot. You can send that fluid out. As long as you're 6 feet underground, what's going to happen is the ground is going to be at pretty consistent 55 °F. And so now this fluid that you have inside the line is going to be extremely cold. The fluid that you would use is typically something like a refrigerant that you would use in a refrigerator. And so this really cold substance is going to be absorbing heat from the ground. 55 degrees, while that's not as warm as you want your house, it's way warmer than this fluid is going to be. So it absorbs all of the heat, heats it back up to 55 degrees, and then you put it back into the house, compress it again, you warm it up to the temperature that you need, and then you blow hot air, the air off of that, and you exchange the heat. And so it uses compression and decompression and exchanging heat with the ground in order to heat your house up to a comfortable level. And this can save 30 to 70% on energy costs when you look at how this works. And the really great thing about this is you can use it in the summer, and the same exact idea, except you use it in reverse, where you're going to decompress in the house and blow the cold air off of it, and then when you put the warmer fluid out into the ground, that heat from the fluid gets transferred into the ground and it absorbs the extra heat. So the same cycle can be used in both directions. Well, that does it for geothermal energy, and now that you've seen all of these different energy sources, we're going to ask you to start thinking about, okay, so under what circumstances would each of these become the best energy source to use? See you in class.